Graphing logarithms. So in the past I talked about how there is a direct relationship between exponentials and logarithms, that they're inverses of each other. And in a previous lesson we talked about how an inverse is actually a reflection about the line x is equal to y. What that means is if we know how to graph our exponential, then we can use that table of values and take the inverse of it, meaning we switch our x and our y values to be able to graph the logarithm. That means we're going to start with identifying our exponential parent function. So in this case, the base of our logarithm is a 3. Y is equal to 3 to the x. So we're going to make the table of values for the exponential parent function. So we set up the table of values, we pick our numbers, -1, 0, and 1, which are the same numbers that we picked when graphing our exponential. Then we plug that into our parent function, so we get 1/3, 1, and 3. The next thing we're going to do is we're going to take the inverse. So we're going to swap the x values and the y values to create the logarithm function. So the new table of values will have x values of 1/3, 1, and 3, and y values of -1, 0, and 1. So notice that the original x's became the new y's and the original y's became the new x's. So this is our table of values for the logarithm base 3 of x. We're going to plot these numbers. So we get 1/3 and -1, 1 and 0, and 3, 1. Now I'm going to pause there for a second to remind you about our exponential function. Over on the left, I've made a really quick sketch of what will be our parent function, which is the exponential. Now the base is a number that's greater than 1, so that means it's going to be a growth. And it's going to go through that point 0, 1. And it will go up and to the right. So just a really quick sketch. Also, I want to remind you that with our exponential function, we have an asymptote that is at y is equal to 0. Our domain is all real numbers, and our range are values greater than 0. Now, why this is important is that what we just graphed, our logarithm, is the inverse of that. And our x values became our y values, and our y values became our x values. So that also means that this asymptote that was originally at y is equal to 0 for our exponential is going to now become an asymptote at x is equal to 0. And that's because it's an inverse. Our x's become our y's become our x's. That also means that our domain and range are going to flip-flop as well. Our domain for our logarithm, notice, is now positive values greater than 0, and our range is all real numbers. So if you look at this, our original domain has become our range, and our original range has become our domain. And again, that's all because our x and our y values have reversed because they're inverses of each other. Now let's finish off with answering the rest of these questions. Our x-intercept is at 1, 0. We already identified our asymptote, and now we have to do our end behavior. So end behavior talks about what is happening as the x values get larger and what is happening when the x values get smaller. So if we look at our right-hand side of the graph, the y values are increasing. So f of x is approaching positive infinity, as x approaches positive infinity. And on the left-hand side, although the left-hand side is being blocked by that asymptote, our y values are pointing towards negative infinity as the x values approach 0. Now we're going to apply the same method of graphing logarithms to one that has transformations. So we'll use the same process. We'll first identify the exponential parent function. So we see that it has a base of 2. So y is equal to 2 to the x. Then we'll make our table of values. So we end up using -1, 0, and 1. If we plug that into our parent function, we get 1/2, 1, and 2. When we make our table of values, we use our x values -1, 0, and 1. We end up getting 1/2, 1, and 2. Then we will switch those x and y values to come up with our table of values for the logarithm, base 2. So we end up having 1/2, 1, and 2 on the left-hand side for the x values, and -1, 0, and 1 on the right-hand side for the y values. Now let's look at our transformations. We have a 1 that is added to the x, so that's going to be a translation left by 1. And then we also have a 2 that's being multiplied in front of the logarithm, so on the outside of the parent function. So that's going to be a vertical dilation. We go down to our table of values and we apply our new expressions. We have x minus 1 and 2y. So we end up getting -1/2, 0, and 1, and then -2, 0, and 2. We have normally an asymptote at x is equal to 0, but that asymptote is also going to be shifted to the left by 1. So our new asymptote is going to be at x is equal to -1. I'm going to graph the rest of my points. So -1/2, -2, 0, 0, and 1, 2. And then I'm going to join those points together and making sure I'm approaching that asymptote line, which helps me shape my graph. The x-intercept is going to be 0, 0. The asymptote we already talked about, which is x is equal to -1. Our domain are numbers greater than -1, and our range is all real numbers. So when it asks how do the asymptote and the x-intercept compare to that of the parent function, both have been shifted to the left by 1 because of that horizontal translation. Here is our natural logarithm. So remember, our natural logarithm is really just log base e, and e is a number that's approximately 2.718. So that means that if we were to graph the exponential, this would appear to be a growth function. If we change that to be a logarithm, and I'm just going to do a sketch just to give you a visual, our natural logarithm would be a reflection about that line, y is equal to x. So it would look something like this. Again, notice that now our asymptote is at x is equal to 0 rather than y is equal to 0. The question says, describe how the graph compares to the natural logarithm. Well, if we look at our transformation, we have something that's added after the parent function. So this is going to be a vertical translation up by 4. The entire green line will just shift up by 4. By shifting up by 4, it will not change the domain and it will not change the range, but it will impact that x-intercept. For our last example, we're going to come up with the equation of the logarithmic function. Now the question is telling us that we have a base of 7. So we're going to start by making the table of values for the parent function of logarithm base 7. So we start with the table of values for the parent function of the exponential, and then we change that into the logarithm base 7 of x, so that parent function for the logarithm, by switching the x and the y values. And by graphing the parent function, we can see how the coordinates have changed between the parent function of the logarithm and our new transformed function of the logarithm. I'm going to start by focusing on the x-intercept. Now notice what has happened to the asymptote. The asymptote has changed from x is equal to 0 with the parent function, and now it's at x is equal to 1. The only way that that could have happened is if there is a horizontal translation to the right by 1. So I'm going to start by putting that into our new equation. The horizontal translation is seen by having that -1 attached to the x inside of the logarithm. You'll notice that the point that was originally 1, 0 has moved to the right by 1 and is now 2, 0. If we add that column onto our table of values, then we would take the 1 that was originally an x, add 1 to it, and it gives us 2. Therefore, if we take that original 7, we add 1 to it, that gives us an x value of 8. Now let's look at this coordinate right here. It actually has an x value of 8. What that means is that we don't have any more horizontal transformations impacting our equation. Every x value was just shifted to the right by 1. Now let's investigate what happens to our y values. The y value of this new coordinate is 3. So the question is, how did the point 7, 1 change to be 8, 3? So we know that there's a 3 here. So what happened to the y value? Well, it looks like the y value was being multiplied by 3. You might wonder, how do we know that the y value was multiplied by 3 rather than shifted up by 2? If the y value was shifted up by 2 and we go back to this middle coordinate, then that means that that 0 would add 2 to the 0, which would end up being a 2. So the point 2, 0 should actually read 2, 2. That's how we know that this is not a vertical translation up by 2, but rather a multiplication by 3. If we take that middle coordinate again, we multiply the 0 by 3, we end up getting 0. Which is the coordinate 2, 0, which is the one that we already identified. Meaning that we have a vertical dilation of 3. When we put that into our equation, it goes right in front of the logarithm, so on the outside of the parent function.